Right. So, first of all, thanks to the organizer for inviting me to speak here in this very nice venue at this very nice conference. So I'm going to talk to you about a recent paper that I'm going to talk about work that I've recently done in collaboration with Federico Ambrosino and that I am currently doing with Federico, Matte, Lenses, and also with Roberto Tateo. And just to give you the references, this is the main article I'm going to be talking about, but also I will mention things about recent work in progress with the people that are listed here. Okay, so let me start with a brief slide on motivations. So as you might know if you saw a previous talk of mine, I am primarily interested in understanding the space of two-dimensional quantum field theories. And in particular, using the RG setup, which identifies fixed point as conformal field theories, and then studying the flows between them, from them, then going somewhere. And in this setup, symmetries are really important as they seem to be everywhere, essentially. In particular, in this RG setup, they act by reducing the infinite dimensionality of the setup. So if you keep on having some kind of infinite space of possible theories, but if you have symmetries in the game, then you can reduce the amount of infinity, in a sense, that you're dealing with, right? Because you want to have theories that respect a certain set of symmetries, so you have to reduce the possible interactions and so on. So that's one naive way in which symmetries are important. But maybe more importantly, they impose selection rules, things like Toft anomaly, matching, and things of the sort. And if you're lucky to have enough symmetries, sometimes they allow you to control the flow, and that's what happens when you have integrability in the game, right? So these are just a few examples of why symmetries are important. And so this is a picture that you probably have already seen. So I just made it smaller, so it's less boring. But we have three principal types of flows that we can have in this RG setup. So we have marginal flows that go from a CFT to another CFT. If you're lucky enough to have a marginal operator, then there is a conformal manifold, and you can use the coupling to that operator to move on the manifold. You have relevant massive flows. So you have flows that start on a UV CFT, you have a relevant operator, and then you turn on the RG machinery, and then this flow usually goes to an empty theory. If you have a mass gap, then the degrees of freedom decouple in the IR, and then you end up with a theory that doesn't have any propagating degrees of freedom. It might have some topological features, but in general, it's an empty theory. And then you also have my favorite flows, the irrelevant flows, which actually are the majority of the possible flows if you're in dimension bigger than 1. So you have an irrelevant operator that you can use to perturb a conformal field theory. Now you cannot think of that as a UV point anymore because of how RG works. But if you insist on following the direction of a specific irrelevant operator, then you can actually try to trace a path in the space of theories, and this is the example of the TT-bar operator, which actually allows you to do it exactly, so you can actually flow that. But, so in a shocking twist, I'm not going to talk about the irrelevant operator, but I'm going to talk about the relevant flows, and in particular, about massless flows. So we know, we have some examples, and I'm going to give them, that there exist flows in which the mass gap is 0, right? So when you take a UV CFT and you perturb it in a certain way, some degrees of freedom survives in the IR. So what happens is that in the IR, you expect to have another fixed point, and that fixed point is a CFT because it has propagating degrees of freedom. It's not an empty theory. Okay. So let me review what we know in 2 dimensions. I didn't mention I will be focusing on 2 dimension. So in 2 dimension, we know some example of massless flow. Probably the most famous one is what is sometimes called the imaginary mass Sine-Gordon theory. So you have an action, the Sine-Gordon action, and Fendley, Salor, and Zamolodchikov, and also Alyosha by itself later, they studied the regime where mu here I put a square root in the coupling. When mu is less than 0, then this coupling becomes imaginary. And in this article, they showed that the beta function is compatible with a massless flow, so a theory that flows to an IR fixed point. While, well, very famously, if mu is bigger than 0, then you get a massive flow, and the theory flows to an empty fixed point. And this theory, you can also perform quantum reduction on the quantum algebra that underlies Sine-Gordon, and you can produce the phi 1,3 massless flows that go from mq plus iq through the field to the relevant field phi 1,3. So the most famous one is the tricriticalizing to Ising flow, which is obtained putting I equal 1 and q equal 4. I'm going to review also the notation here, but this m just simply means minimal model with p and q as written here. So this is an example, but we have other examples. And Doridani and Tateo in 2000, they showed that you can define, well, you can control using integrability these two types of flows. So flows that are issued by the field phi 1,5 and by the field phi 1,2, and they interpolate between these these classes of minimal models in this way. And one thing that, so what the method that they used, they started from the ODIM correspondence. So they had some information on the massive version of these flows, and then they conjectured a Destri-de-Vega equation for that. They studied that, and they saw that it corresponds with previous conjectures on the existence of this flow. But the question remains that can we interpret them in the same way as for the imaginary mass Sine-Gordon as an imaginary mass version of the Gibber-Mikhailov-Shabat model, which essentially is the Bullock dot model, which has this action here. So can we use quantum reduction to construct this massless flow from this theory where mu is less than 0? This, as far as I know, is an open question. I might be wrong about that, but I didn't find any information on that. Well, we know that we can do quantum reduction on the version for mu bigger than 0. I'm talking about the imaginary mass version. Okay, so this is what is known from integrability, but recently there has been some interest in other types of flow. So Klebanov and collaborators, they were interested in studying these UV theory, M103, so this minimal model, perturbed by a field phi 1,7. Now, in principle, this field is not supposed to be, these theories, this deformation is not supposed to be integrable. Okay? We can do some counting argument, and the counting argument is inconclusive. We cannot conclude that the theory is integrable. But nonetheless, they had some argument using some anomaly matching, saying that this flow, if it exists, it should flow to this minimal model M83. Okay, and then they extended the analysis, and they studied this class of model, this one-parameter family of models, also perturbed with phi 1,7, that it's supposed to flow to this IR here. And then even more recently, in 2024, slightly more recently than this one, Tanaka and Nakayama conjectured a two-parameter family of flows that now is generated by the field phi 1 to k plus 1, where k is an integer, but it can also be an alpha integer. There are some technicalities here that I'm not going to go into. So there seems to be a whole host of massless flows. But all of these flows are conjectured. There is no explicit proof of their existence. There are strong conjectures, but they're still conjectures. And so, well, mimicking what I said before, we can ask, do these arise from some kind of imaginary mass version of, this time, Liouville field theory? Because if we think about generalized minimal models, where we have Liouville theory that describes the UV theory, with some central charge that is dictated by the parameters of the system, if we do this interpretation of this action as being the UV theory, we can identify the field phi 1 to k plus 1 with this exponential here, where m is related to k by a linear relation. And the question then is, if I put mu less than 0, can I, by doing quantum reduction, reproduce these flows? But of course, I'm not going to answer to this question. This is a question that is out there, and I hope at some point we might be able to answer that. Okay, so this is more or less what is known in 2D about massless flows between minimal models. One important thing that I want to stress is that this conjecture here, the conjecture of the existence of these flows by Tanaka and Nakayama, was done based on these flows preserving something which is called modular tensor categories, essentially these non-invertible symmetries that you might have heard about, and I'm going to review them in a moment. The idea is that these operator here, preserve a subclass of all the possible non-invertible symmetries in this theory, and you go and scan which are the possible IR that also have that category. And they identified these IR here. Okay, so for this reason, let me just very briefly and very probably sloppily introduce you to generalized symmetries if you don't know them already. But the idea is actually pretty simple. So the idea is to go back to the definition of global symmetries. They are unitary operators. They act on a Hilbert space, which usually is defined by just slicing along a time direction, our space-time. So we fix t, and at each t we have operators that we have operators O, we have a Hilbert space, and then we have unitary operators that act on these Hilbert space. And the additional requirement for these to be global symmetries is that we want them to be conserved on time. So we can move the time slice, we can move on the time slice, and the U will always be the same. Okay? It doesn't evolve in time. And also note that U acts on all space-time, all space points, sorry, and it's defined on this codimension 1 Cauchy slice. Okay? So the picture is somewhat something like that. You have an operator here, and then you can, since U is conserved in time, you can think of defining it on 2 time slices, which are far from that, and then you just sandwich it inside, with the operator inside, and what you get out is a deformed operator. It can be a rotated operator, it can be another kind of operator, depending on the symmetry and on the operator you're considering. But the important thing is that you can, if you just move away from the idea of slicing along the time direction for a moment, you can think of this action as being essentially a codimension 1 surface that surrounds your operator and acts on that by this chain, by this chaining. Okay? So we can interpret this if the idea is that we move from some kind of space-time picture to a Euclidean point of view. Now all time and space are essentially on the same ground, and so we don't have a natural Cauchy, we don't necessarily have a natural Cauchy slicing. So it is more general to say that these operators are defined on a codimension 1 manifold, which can be general. The important thing is that they are conserved. So when we deform the manifold without intersecting any insertion in your space-time, they will be the same. They won't change. But now if we take this point of view, and this is meaningful because it reproduces the usual definition of global symmetries, we can actually generalize the definition. So we start from saying the standard global symmetry is topological because I can deform the surface, invertible because there exists an inverse, and codimension 1 operator. So operator defined on a codimension 1 surface. But we can think of dropping some of these assumptions, right? So we don't really want to drop the topological part because that's what makes the object a symmetry. But we can drop the invertibility condition, and this brings us to the non-invertible symmetries. So these are symmetries that do not necessarily have an inverse, and I'm going to give you an example later. Or we can drop the codimension 1, we can change it and actually consider operator defined on a higher codimension surface, and these are the higher form symmetries. Now in this talk I will be focusing on non-invertible symmetries specifically, and specifically in 2-dimensional conformal field theories. Okay. So let me give some notation for CFT. So all this is introduction notation and things like that, and I will give you some result later. So as I said before, this symbol denotes a minimal model. PQ are 2 integers, which are bigger or equal to 2, and I choose these disordering. So P is bigger than Q. That's not the usual one, but it's easier for me because well, there is no real reason. I can just rearrange them and the formula will remain the same and just need to switch the parameters. But this is the way that I chose it. And the central charge is, as you all know, this one. And in this minimal model, there exists P minus 1, Q minus 1 over 2 primaries. The primaries are denoted by phi rs. R goes from 1 to Q minus 1, S goes from 1 to P minus 1, and this is the conformal dimension. Okay, so this is all pretty familiar stuff. But an important thing is that all these primaries, they satisfy some kind of Verlinde algebra. Well, not some kind, the Verlinde algebra, which is not properly an algebra. It's more a fusion ring, really, because you don't have only one term here. You have a sum of terms, right? So the bracket here denotes conformal families. As you all know, you have a primary, you have all the descendants. Primary plus descendants is a conformal family, and it's denoted by a square bracket. Here, rho, sigma, and kappa are pair of indices, R and S. And when you do the OPE of two operators belonging to two conformal families, you will find out that you get a sum over operators of other conformal families with fixed coefficients, which are these curly n. Okay, so this is also well known, but it's important because this expression here has the same form of what you find when you study non-invertible symmetries. This is a fusion ring, which is the same mathematical structure. Okay, so one can think, and this was reviewed in this article, it was actually thought earlier than that, but this review is quite clear on the math that is going on. We can think of taking each family and associate with that a Verlinde line. So an operator defined on a line, which I call curly L rho, where rho is the subscript. And this line acts, like I said before, by chaining on operators in this way. So it acts on state on a cylinder. The state on a cylinder is generated. In this case, I use a primary, but I can also use a descendant. And then the action of L on this operator is just given by this line, which is just a factor of two modular S matrices. And the modular S matrices are objects that you can use to build this curly n, the Verlinde coefficients. Okay? They are tabulated, they are numbers. Nothing fancy. Okay. So this I can define this operator, and if I go and see what happens when I act successively with two operators, because of how are they defined, they satisfy the same algebra, the same Verlinde algebra that I showed you before. Or better to say, they satisfy a modular fusion category. Or they form a modular fusion category. Okay? So these lines are these non-invertible symmetry lines. And I'm going to show you in a very simple example that they really are non-invertible. Okay, in Ising model, you have this structure, and one of the lines is a non-invertible line. So the example, if you take Ising, how does it work? You have three primary fields, so you have three families. One is the identity, one is the spin, one is the energy. They have these dimensions here, as you all know. And then I take each one of them, and I associate a line with each one of them. One is the identity line. Sigma gets associated with the line D, which is the Kramer-Spanier line. And epsilon gets associated with eta, which is the energy line in a sense. And now if you go and check, if you take the big yellow book and check the Verlinde algebra for this case, you will see that the line behave like this. So eta contracts with itself in the identity. But importantly, this Kramer-Spanier line contracts with itself with the identity plus an energy line. So if you think a moment about what this says, it's saying that when you take an operator, any operator O, and you act on it with a line, with a Kramer-Spanier line, you will end up with an operator that has a tail. So you end up in a twisted Hilbert space. So what does this line is it maps local operators to disorder operators. That's what the Kramer-Spanier duality does in Ising, right? And the Kramer-Spanier duality in a CFT is really a symmetry of the system, because Kramer-Spanier maps the low temperature to high temperature Ising model, but if you are in a CFT, you're at a self-dual point, so that's a symmetry of the system, right? It's a weird symmetry, but it's still a symmetry. It's a non-invertible symmetry. Okay, so this is just one example. You can go and check your favorite minimal model. They will all have, all of them, they will have these structures. And crucially, these structures are very, very much like a fingerprint. They are all different from one another. So they kind of identify the minimal model that you're looking at. And just for information, this is called the Z2 Tambarai-Yamagami category. Okay, so just keep that in mind. I'm going to return that briefly in a moment. But let's return to what's the topic of the talk. We want to consider a relevant deformation of this form. So we have an action, a minimal model action, and we just perturb it with a relevant field, okay? With a coupling G. And now what we want this action to describe a flow that goes from a UV. We know that this describes the flow from a UV, because this is a relevant deformation, but we want that on top to go to an IR CFT, which is a non-trivial CFT. This is a massless flow. That's what we're searching for. And a few things to notice is that in this action, in this expression, there might be more relevant operators that appear. This is what Wilson tells us. We need to add all of the possible relevant operators and then check how they behave under the RG flow. So it might very well be that this is just a description, infinitesimal description out of the UV, but to actually get to the IR, I need other relevant operators to be added to the theory. And another thing which is important is that the effective central charge of the UV has to be bigger than the effective central charge in the IR. Now, it doesn't necessarily have to be monotone, because this is not the Zamolodchikov-C function. It's a different function, but it equates Zamolodchikov-C function in a CFT. So this means that it can oscillate, but in the UV it needs to be bigger than the IR. Or if you want, another way to say is that the number of degrees of freedom in the UV has to be bigger than the number of degrees of freedom in the IR. Okay? Good. So this is the way that I will denote it, very simply. MM with an arrow and phi. Okay, now take that, take the UV, and then suppose that in the UV, we choose the deforming field so that there are a set of lines, set of Verlinde lines that commute with that. So we choose, we just check which are the lines that commute with the flow. And suppose we find a bunch of them, and suppose and then finding a bunch of them, we collect them into a maximal set of lines that is also closed under fusion. So it's a subcategory, okay? We start from a larger category. Some of the lines will not commute. We select the maximal amount of line that closes under fusion, okay? Now, this object here, since all the line commutes with the deforming operator, it will be preserved along the flow, right? So we need to find this same category, this same subcategory in the IR. It can be a subcategory in the IR, so there can be an enhancement. We can have more lines in the IR, but this object C has to be contained inside the IR. Now, it turns out that this condition is incredibly constraining. And this is the procedure that was done by Tanaka and Nakayama that we sort of automatize in a sense. And essentially uniquely pin down the allowed IR. And in doing so, it uniquely pinned down the possible massless flows, right? And also one thing to be noted is that this is not a positive statement, this is a negative one. So what this does, it prohibits a certain flow from existing because there is no matching between the modular categories, okay? But it doesn't actually tell you that the flow exists. The flow may exist. Now, you can say, okay, if a flow is allowed to exist and it doesn't exist, then you should give me some reason why it doesn't, right? There should be some reason why a flow that might exist doesn't. But still, I cannot claim that the flow that I am showing you, these ones, they actually exist. I'm just claiming that they might exist. So this is just to show you the complexity. We have very many, for example, flows that start from M78, which is unitary. We have a lot of flows. These ones are the usual phi-13 flows, the one that go along this line. But then we have many other ones that are allowed to exist. Okay? Good. So this is the first part, and this is essentially what Tanaka and Nakayama did. Nothing new. Now, what's new, okay, I'm going to speed up slightly here, but what we found out is that there exists a description, an NLIE description, something like a DDV equation, that appears to encode the ground state energy of all the flows that I showed you before. This is, again, an assumption. I'm going to return to that later. But essentially, the idea, just to give you an idea of what an NLIE is, for those who don't know, the NLIE is a way to encode the dependence of the energy, energy of a state on a cylinder, on the radius. Now, we know that the energy in these cases should have this limiting behavior. In the UV, it should go to the CUV minus 24H, where HS tells you which is the perturbing field, and the same thing should happen in the IR. We fix the mass scale. Well, I mean, this is all technical, but essentially these are the equations. So you have the energy. The energy is defined as some kind of integral of some functions, and these functions have to solve this coupled pair of equations. Okay, this is the massless version of the usual Destri-de-Vega equation, and this is the definition of L. Okay, this is just to just briefly show the type of equation we're dealing with. It's very similar to the TBA equation. It's a different approach, but it's a similar concept. And now, the important thing is the data that we have here. The data consists of two contours in the complex plane, and these contours are the ones that tell you which is the state on the cylinder that we're looking at. In particular, for the ground state, these lines are just slightly above and slightly below the real line. So they are simple contours. If you consider excited state, they can be more complicated contours, but we will focus on those. And the rest of the data, it consists of a twist, which is a real number, and two kernels, phi and chi, that appear in the integral equation. Okay? And these determine the specific theory that we're dealing with, because these are the ones that constrain the UV CFT, the IR CFT, and the perturbing fields. And what we did was to conjecture to a two-parameter family of kernels, which are these ones. And I conjectured them following a number of arguments. I wanted them to be bounded. I wanted them to define functions and not distributions. I wanted them to have this cosh, because this cosh reproduces the bulk energy. So there are a number of assumptions that go into that. But crucially, I didn't assume them to reproduce the known kernels for the DDV for phi 1.5 or for phi 1.3. Okay? This is something that I found out later that it's the case. So that's an assumption. And when I have 2 plus 1 parameter, the 2 in the kernel and alpha, I can fix 3 quantities. So I can fix the UV and IR effective central charge in this way, and the deforming field in the UV. And this Z is just a 1 or 2, depending on the field being odd or even. It's just a quantity. It's nothing too fancy. So these 3 are input data. I start with a flow that I suppose might exist. I start from a UV, from a deforming field, and I say, okay, I have an IR. I fix these 3 quantities, and then as a check, I can go and see if HIR, which I can also compute from the DDV, does belong to the CATS table of the IR CFT. And this constrains the possible values of kappa and psi that I can have. And what I find is that I find some Diophantine constraint. If I assume that Z is conserved along the line, this is the equation that I find. If I don't, it's slightly more complicated. But these constrain the possible pairs of UV and IR CFT that I can have. And what I find is that the Tanaka-Nakayama family is contained in that. And moreover, all the families of CFT that I find are the ones that we found with non-invertible symmetries. In particular, this is one example. So there seems to be something here, because I didn't input any information on non-invertible symmetries here. I just find the same exact set of flows that I would find using non-invertible symmetries. And additionally, one other thing that we find is that if we do numerical analysis, we find that the theory really doesn't only contain the first relevant operator, the one that is dictated by this dimension here. So this is a fixed one. This is the most relevant operator that appears in the UV. But as I said before, there might be subleading terms. And numerical analysis tells us that we should really add also these two. For example, in 517, we should also add these two. And if we go and look at the commutation of these fields with the non-invertible line, we find that all three, if I choose the lines as the one commuting with 517, then 515 and 513 also commute with all those lines. So they also are allowed on the flow. You can have them because they don't break the non-invertible symmetry. So this is also another non-trivial check that something is going on. And this is an example of the numerics that we did. One thing that I should say, the numeric is kind of low precision. It's enough to give us some confidence that this fit tells us that we need 517 and 513. Here 515 has the same dimension of 517, so it doesn't explicitly appear. But this really suggests that since this line is much more precise than this one, you really have to include subleading terms, okay? Right. So one thing, I will conclude with that. One thing that is important to remark is that I am not claiming that the theories, these flows, are integrable. At the moment, I don't feel confident enough in saying that because on one side, we don't have precise enough numerics to do, for example, comparison with CPT. It's something that we're doing at the moment with Roberto. So I hope to be able to say something in the future about that. So I don't feel confident in saying that, also because there might be reason why this function is not exactly the ground state energy along the flow. It only flows to the exact energy in the CFT point. And that's because in the CFT, we recover integrability. So the idea, for example, if you think about it, if you think of the kernels as somehow having to do with the two-body scattering of some theory, if this theory is non-integrable, the two-body scattering is not the whole physics, right? You need to include higher particle scattering, particle production. So it might be the case, and this is a guess, that this encodes only the two-particle physics of some theory, and to have the actual ground state energy, you will need to include further terms. So this is just one way the things could go to sort of, okay, well, this is something that might be, and you can ask about that. But this is a list of things that we want to do. It's a short list of things we want to do, and yeah, so thank you very much.
So before question, because people may start dissipating, so according to Google, there is some kind of sun outside, so we'll be taking a group picture outside right after the questions. Don't run away.
Questions?
Would it be interesting to study the RG flows between minimum models with additional W symmetry?
Oh, yeah. In principle, you can. And I think you would have to consider not just one equation for the DDV, but more than one. Like when you consider, in a massive case, when you consider AN structures, you will get N DDV equations, and they will have a central charge which is larger than 1, so you can identify them with this W symmetry thing. So yeah, I think it's possible. It's just, I mean, we have a lot of problems with this already, so yeah, and that's in the future.
More questions? Okay, let's thank Stefano again.
Okay, thank you.